Lecture 15 today. We shall be starting a new topic of MESFET, metal semiconductor field effect transistors. These have been the workhorse of analog microwave electronics for a long time. Even today they are very widely used in many applications. So the next 6 lectures or this week will be on gallium arsenide MESFETs typically, and then the next week we will study about HEMTs and then pseudomorphic HEMTs the week after. However, many of the discussions in the 3-5 compound semiconductor FETs are actually relevant that we are going to do in MESFET will be also relevant to HEMTs and pseudomorphic HEMTs. So many of the microwave engineering concepts and in terms of the device layout and design that we discuss in MESFETs are also readily applicable to HEMTs and pseudomorphic HEMTs that we shall be talking about. So many of these things will be intermixed in this week and the next 2 weeks, but we should keep that in mind. Okay. So we will shift to the whiteboard here. So we will start the topic of MESFET, as you can see, and MESFET actually are typically made of gallium arsenide, which is a compound semiconductor, and compound semiconductors, as we know, are very critical for a large number of microwave applications. So when we say 3-5, we typically mean the gallium arsenide family, the gallium arsenide indium phosphide family essentially. We have L-gas, L-gap, IN-gap, IN-gas, etc., etc. So the 3-5 compound semiconductors. Typically they have a MESFET. We can make MESFETs, which is what we shall discuss this week. You can also make modulation doping FET or called HEMTs, which can be categorized into pseudomorphic HEMT and metamorphic HEMT. What are those? We shall talk about in the next 2 weeks, but for this week we will focus on MESFET. It is the simplest of all. Actually you can see an image here, you see an image here. It might look a little bit exotic, but actually it is an image of a microwave gallium arsenide MESFET. You can see there it is like interdigitated fingers are there. So you can be assured that these are actually source and drain fingers. Each of this could be source, for instance, the other ones could be drain, and in between you will have gate that runs. You need so many fingers to carry higher current because you need to deliver higher output power, and the metals are also thick metals because they should be able to carry high current. Okay? Alright, only then you can get high output power. So this MESFET, we will come to the physics and the structure of MESFET in a short while, but in general 3-5 compound semiconductor FETs, which include MESFETs and HEMTs, they give excellent performance as power amplifier, low noise amplifier, and also mixers, and many MMICs are being made based on this material system, these devices. And MESFET actually is the simplest of all. It is relatively simpler to grow the material stack or to also fab compared to pseudomorphic or metamorphic HEMTs. MESFETs also give good linearity, we will see later how. Linearity is an important property that is desired in many RF system, and MESFETs are good for inherent linearity, and many of the legacy systems, which means historically many of the systems in the space or strategic sectors still continue to be using MESFETs because of the bigger bulk systems still use MESFETs today. So in general, when you go for a modulation doping HEMT, which is a little bit more complicated, you get better high frequency performance, you can get higher power, better noise, but it is also a little bit more costly and more complicated to achieve or make HEMTs compared to MESFET. Okay. As I started this lecture by saying that many of the design concepts, many of the concepts in terms of how to make this, for instance this is a big device, how to make this big device, why so many fingers, what are the design considerations, what are the aspects of noise or power, all those things are very similar or almost the same for any kind of FET, whether it is MESFET or HEMT or even MOSFET for that matter, or we will see in gallium nitride HEMT later on. Many of these concepts are very similar, so we should keep that in mind. So when we discuss them here in the context of gallium arsenide, it is just not gallium arsenide MESFET, we can use them also in case of HEMTs. Okay. So with that background, we shall come to the device physics and the working of MESFET, okay, in gallium arsenide MESFETs. So you see MESFET is the simplest structure. You have metal electrodes on two sides which are source and drain, and then you have a gate. The gate forms a Schottky contact. Okay, the gate forms a Schottky contact. So because it forms a Schottky contact with the material, and this is say n-type doped gallium arsenide, the reason people use only n-type is because in p-type material the whole mobility is pretty poor. So and if you have just n, you can get just unipolar device, which means there is only one type of carrier which is electron, and so these are faster and the noise performance is also better. You have only one type of carrier. So whenever you put a Schottky contact on a n-type doped gallium arsenide, for instance, you will have some depletion around it. It is a natural, at zero bias gate voltage you will have some built in depletion. Okay. and as you keep increasing the reverse bias on this, say you go to minus 0.5 volt, minus 1 volt, minus 2 volt, etc., your depletion will keep extending because you are applying more and more negative voltage. At one point the entire channel will be depleted, okay, in which case the electrons from source will not be able to go to the drain and the device will be off. So, the gate actually is controlling the carrier density in the channel, and gate, by applying a sufficiently negative bias on the gate, you can turn the device off, okay, and when you turn the device on, you apply bias accordingly. Okay. You cannot apply too high a positive voltage plus 1 plus 2 etc., because this gate will start leaking. Okay. The gate, because it is a Schottky contact, if you look at the Schottky contact, it looks something like that, correct. So, if you apply forward bias, then this Schottky will start leaking. You know, if you remember a Schottky bias behavior, it looks like something like that, correct. So, you are operating in this part where the gate should not, this is the gate Schottky, it should not leak or leak very low, you know, should not leak. This part is where the gate will turn on, and so the gate will start feeding a lot of electrons here, and that will not be useful to the device. So, you cannot apply on too much positive voltage on this kind of a structure. But this is a very simplistic layout. We of course have to talk about in more details about how this works as a 3 terminal device. So, imagine, I mean, this is said p type, but it is mostly n type. So, you have an n type semiconductor, but it is on below that you have something which is semi insulating. Imagine that there is something semi insulating, which means it is highly resistive, there is no conductivity across this layer. It could be a substrate for instance, or it could be some other layer. Okay. On top of that you have this n type doped gallium arsenide, and of course, you know, for source and drain you typically have a highly n type doped region n plus, so that your contact resistance becomes lower, because anytime you put a metal in contact with semiconductor, there is always a contact resistance that drops. So, to minimize the contact resistance, you can have a highly doped n plus pocket, n plus pocket as a source and drain. We will come to that later when you discuss about fabrication, but in general this is your channel, correct, this is your channel, and you can apply gate bias to pinch the channel off, because the depletion will keep extending, right. So, you can see this is the energy band diagram, this is the conduction band, this is the valence band, and this is the Fermi level you can see. So, you know, substrate is insulating, so the Fermi level is almost at the middle of the band gap, correct, because this is almost insulating. Okay. So, there is no conductivity that can happen through the substrate. Now, this is your this H you see here, it says H, this H is the channel, this is the H, this entire channel is the thickness H. Okay. Different books use different terms, we will use that also. So, this is H, and you can see that at a given bias or maybe at 0 bias, some part of this is depleted. So, this is your depleted part. Okay, this is depleted of carriers, and this is where the active channel lies, okay, where does this not depleted. This is which will carry the electricity, or which will carry the current. Okay. So, the more negative voltage you apply, minus 3 volt, minus 4 volt etc., the more you push this up and more you deplete this. So, this channel thickness becomes reduced and eventually it becomes 0, and then the channel turns off. Okay, the channel turns off. So, that is in a way the principle of how this device works in terms of a transistor. How it will amplify we will see, of course. So, we will have to look at, that was only at the gate bias, what we do at the gate bias. Now, of course, in a real transistor you have a drain bias also, we call it VD. So, the drain bias will modify the 2 dimensional electric field profile and the way the carriers transport. So, it is a bit more complicated, but if we do not go into the math, if we just look at qualitatively how the drain voltage is going to affect this channel, then you see at when the drain voltage is very small, it does not matter as much, the gate will control the channel, of course. At 0 voltage on the gate you have certain depletion, this is the channel which the electrons will go in this channel, right. As you apply more and more negative voltage, this channel will become less and less, and eventually the channel will turn off, correct. So, this is at low VDS, this is all at low VDS, at low VDS. So, this is your output characteristics, you are plotting the output current ID versus the output voltage VD in all of this, you are plotting the same thing. So, at low voltage on the VD, when your channel is on, your current has a linear slope, of course. When you keep increasing the negative bias on the gate, minus 1, minus 2 etc., then your current will keep coming down. So, that is why you have a lower slope and the current keeps coming down, coming down, coming down, eventually the current will change, you know, become almost 0, the channel is turned off, you know, it is called pinch off. So, now you have to imagine that if I take a material which is n type dope, and suppose this thickness is H, it is suppose n type doped with a doping density of Nd, and I assume 100% ionization of the dopants, then if I put a metal here, imagine I am putting a Schottky metal, the amount of total voltage that I need to apply to deplete this entire region. This entire region can be depleted when I apply this voltage, which is Q times the doping times the thickness square divided by 2 epsilon naught epsilon s, where epsilon s is the dielectric constant of the material, which is gallium arsenide in this case. So, this is the total voltage drop that will happen. If you remember, your Schottky barrier looks like that, correct. Schottky barrier looks like that. So, this is your voltage drop. So, to deplete this entire channel, this is the voltage drop you need to sustain across the material, across the channel. However, a part of that is already depleted because at 0 bias. At 0 gate bias or at equilibrium, the Schottky metal already depletes something, right. So, at 0 gate bias, for instance, at 0 gate bias you have a certain depletion, you have a certain built in voltage, we call it built in voltage. Suppose the built in voltage is suppose 1 volt. So, that is the 1 volt that is dropping even at 0 gate voltage. Now, you need suppose 4 volt, you need to drop 4 volt to completely deplete this channel, which means your gate should go to minus 3 volt. Why? Because at 0 volt on the gate you are already having 1 volt drop on the channel. You see, this is your 0. So, there is already some depletion. That depletion is sustaining a built in voltage of 1 volt. Suppose that means the rest of the channel, which is this, to deplete that you need to apply minus 3 volt on the gate, okay, negative 3 volt on the gate. So, that entire thing will be depleted. This is assuming the entire region takes 4 volt to deplete. Okay. So, I hope that is clear. So, this is how this is called a pinch off voltage, but pinch off voltage basically tells you what is the total voltage that can drop across the channel to deplete it, and the threshold voltage will of course be the built in voltage minus the pinch off voltage. So, that is minus 3 volt in this case. Okay. Now, when you apply a slightly higher drain voltage, the drain voltage will start modifying the depletion region. Why? Because you apply, suppose the gate was at certain voltage, say minus 1 volt. If the drain is at 1 volt for instance, or maybe 2 volt, with respect to drain, the gate is at actually minus 2 or minus 3 volt. This minus 1 volt is with respect to 0. So, the moment you apply a drain voltage, this edge is called the drain edge of the gate, correct, the drain edge of the gate. So, this edge will see a negative volt, this is the edge of the gate metal which is closest to the drain. So, the drain edge of the gate metal, it will see a voltage drop of minus 1 or minus 2 volt with respect to the drain, which means this part is more reverse biased, right, it is more reverse biased, and that is why the depletion on this side, the depletion on that side will be more, because the drain is depleting that, right, the drain is depleting that. Okay. Whereas on the source side the depletion will be very low or close to 0, because the source is at ground at 0. So, that whatever gate voltage you are applying is with respect to the source. Okay. So, that is why the depletion has an asymmetric shape here. It has it's very low late drain bias, it is not doesn't matter, but as the drain bias increases it has an asymmetric shape, because the drain with respect to the drain, the edge of the metal will be more negatively biased. So, at sufficiently high drain bias, you know, it's an asymmetric looking depletion width, you can see it will get pinched off near this gate edge of the drain, the drain edge of the gate. This is the drain edge of the gate metal, this is the drain edge of the gate metal. So, at that point your channel depletion will be so much that it will pinch off the channel, which means the current cannot go from the source to the drain. On the source side it does not pinch off, on the drain side it pinches off. So, once it pinches off, if I plot the drain current with respect to the drain voltage, then the current will saturate like that. This part is called saturation. The current saturate, once the pinch off has happened, the current will saturate. Okay. Before pinch off the current keeps increasing with respect to the drain bias, keep increasing, and once it crosses that point it will saturate. So, this is at a certain gate voltage, say minus 1 volt. At minus 2 volt it will be something like that. At minus 0.5 volt maybe it is something like that. At 0 volt it will be something like that. So, that is your classic output characteristics. Okay. And it is important to understand that this pinching off of the channel, this pinch off of the channel that is happening and the current that is saturating, this relation is universal for all types of field effect transistor, you know, a HEMT, a MOSFET, JFET, MESFET, etc. This concept of current saturating and the channel pinching off is universal, in the sense that on the drain side the channel will become pinched off, almost 0, and so the current will saturate at that point. But what exactly happens at pinch off? How does the cross sectional view of a channel looks like during pinch off? Does it completely turn off? If it completely turns off and the if the gate voltage is say minus some volt, minus 3 volt or minus 4 volt, then it has completely turned off and the current will be 0, current will be 0 here. However, if the gate voltage is as I said, if the gate voltage is say not minus 3 volt, but it is suppose 0 volt. If the gate voltage is 0 volt and the channel pinches off here, the current will saturate, the current will be high, this could be say 20-30 milliamps. The current is not, the transistor is not off, the current just saturates here, okay, the current just saturates here, and that is very remarkable because the channel thickness has been reduced to 0 by the gate, but because the drain voltage is higher than a certain threshold, certain it is enabling pinch off, the device actually current saturates. How is it possible that the channel thickness has become 0 and the current has not gone to 0, but the current has saturated? So, it is very important to understand the physics underlying this. Okay. I will quickly come to that and then I will come to the derivation actually. Okay. I will come to the derivation quickly back, but I will actually come to the point where you have this channel pinch off and the universality of the current saturation. So, I will come back to the slides, okay, I will quickly. So, if you look at this image, when you actually get pinch off voltage, when you go to the pinch, when I say pinch off, the channel pinch off, not the gate pinch off, I am talking about the channel pinch off above a certain drain voltage. Above a certain drain voltage the current saturates, we call that the thickness, the depletion layer thickness has pinched the channel off, but in reality it is not a 0 thickness. In reality there is a small amount of opening remaining which is called delta, amount delta. That small amount of opening is remaining here, provided the gate is not completely pinched off. See, if you apply a sufficiently high negative voltage on the gate, then the channel will be literally pinched off, there will be no thickness of opening and the current will become 0, close to 0. However, if the gate is of a certain value which is not pinch off, then the drain pinch off or the drain voltage being at a certain higher value will only lead to saturation of the current, because the channel literally does not become 0, the thickness does not become 0, the thickness is very small, it is called delta. Why? Because if your thickness becomes 0, which means the current the current is basically a product of the charge times velocity. If your thickness becomes 0, if your charge density becomes 0, then your velocity has to go to infinity, which is not possible. The velocity can only go to Vsat, maximum velocity the carriers can go is the saturation velocity of electron. So, at this point the electrons locally travel at the electron saturation velocity, but not throughout the channel, only at that point, that critical point locally the electrons will tend to flow at a saturation electron velocity, okay, which means the current density you will get is limited, there is a limit to the current density you will get and the thickness of the opening that you will get. This opening cannot become 0 arbitrarily small, because the current continuity has to be maintained. So, what people have done is that people have done a mathematical analysis of this. We are not going to solve that, by the way, but it so happens that once you hit the drain pinch off, where you are at a sufficiently higher drain voltage, you can what will happen is that beyond any voltage that you apply beyond the saturation voltage. So, suppose your current is saturating this is the saturation, right, this is the saturation. So, all the voltage that you are applying beyond the saturation, this voltage will be actually dropping in this part, okay. It will drop in this part and the effective channel will become slightly shorter, that is called channel length modulation, but that does not become apparent when you have a longer channel, it becomes apparent only when you have a very short channel, okay. So, the mathematical analysis of this basically follows that you have to solve a differential equation whose solution is given here, but we will not go into the details of the solution. The qualitative understanding of this is that while the field is dropping mostly linearly across this entire gate length, at the edge of the gate the field drops hyperbolically, which means for a very small change in the depletion along this edge, along the gate drain edge, a large voltage can be accommodated, okay. So, any voltage that you apply beyond the saturation voltage, okay. So, this was what I said, that this is the saturation voltage, the current is saturating, any voltage that you are applying beyond the saturated voltage is accommodated by the edge of depletion on the gate metal side and it extends towards the gate drain depletion side here, but a small area or a region in that portion can sustain a significantly large voltage, because the field varies hyperbolically as opposed to linearly. So, you can actually have a large voltage drop in a very small opening, okay. That is what it means. So, as that is what precisely I am saying, anything beyond saturation voltage are absorbed efficiently in a very small region of the second part of the gate, okay, the edge of the gate basically, and this holds true for any type of FET, MOSFET, HEMT, MOTFET, etc., JFET, etc., okay. And that is why the current will saturate and any extra voltage is dropping here. This part, the first part, is actually the channel, the actual channel, and that length of the actual channel does not change much for a long channel device, and that is why the current changes. But if it is a short channel device, which is what in microwave devices we look at, then the current will not tend to saturate, but the current will tend to slightly increase like this. It is called output conductance, and that is not good. So, there are ways to mitigate that with better carrier confinement and things like that, but to a first order, this is the universality of the electrostatics of FET, that the channel pinches off near the drain at a sufficiently high bias on the drain. Beyond that, all the voltage drops in a very small region in the gate drain extension, okay, and the channel length for a long channel device is pretty much the gate length, okay. So, that the current, that is why does not change in the saturation regime. And also we should keep in mind that the channel thickness literally does not go to 0 when the drain pinch off happens. There is a small opening that is there because the velocity saturation is, there is a limit. So, the carrier density that is available to carry current is also, there is a limit. So, you cannot make it 0 and expect the velocity to be infinite. This is all assuming the gate voltage is at a certain bias such that the channel is channel exists below the gate. The drain is merely pinching it off, but the channel exists below the gate, okay. So, however, if in this previous example we talked that there is a -3 volt on the gate can pinch up the channel completely, which means it can turn the channel off. If you apply a gate voltage of -3 volt, then the channel will be literally off, which means the thickness that is remaining in the channel will be actually 0, and in that case the current will also be 0 and the channel has turned off, and in that case even if you apply a drain voltage, the current will still be 0, and you keep applying a drain voltage higher and higher, eventually the device will break down. That is how we define 3 terminal breakdown, but a drain voltage will not be able to conduct electricity in the channel if the gate is at, we can call it threshold voltage, because the pinch off is the total drop in the channel, okay, in this case +4 volt, and -3 volt is the threshold voltage we can say. So, what I say is that if I am plotting the output characteristics ID with respect to the input voltage Vg, then this is -1, -2, -3. At -3 the channel will turn off, at -3 the channel will turn on the other side and the current will increase, okay. So, -3 is the threshold voltage, we can call it VTH, the threshold voltage. Below -3 the channel is off, no matter what your gate drain bias is, provided it is lower than the 3 terminal breakdown, okay. However, when the gate is not lower than -3, but it is somewhere in this range from 0 to -3, then the drain voltage can pinch the channel off locally near the drain, but it does not mean the channel has become 0 thickness. I have been repeating this statement because it is the most important part to understand how actually the current saturates in an FET, in a field effect transistor. This picture precisely says that there is a narrow opening here where the only locally the carriers go at velocity saturation. The carriers do not go at velocity saturation throughout the channel, they only go locally here, okay. The drain is pinching off, and the thickness of this width or the width of this channel is basically the total current that you are conducting divided by the charge times velocity, okay, the charge times velocity. I will come to transconductance quickly. So, this is the reason why the current saturates in this way, the current will saturate in this way, okay. The current saturates once your drain is pinched off, not the gate, okay. So, the current will saturate here, alright. This image is taken from the book by Professor Umesh Mishra and Jasprit Singh, it is a very good book, and then you can see that if we take a long channel device where the L is few microns for instance, and this is not very useful for microwave devices, but to understand the physics of the device it is okay to take it as a long channel device. In a long channel device you can use GCA, which is the gradual channel approximation. So, the gradual channel approximation says that the field will vary gradually along the channel, okay. The field will vary gradually along the channel, and essentially it is a long channel device where mobility is independent of this x, okay. But in this case they are considering this as the x, this direction as the x, okay, for this particular image. Okay. So you are using the gradual channel approximation where the field is varying gradually across the channel length here. Now if your total channel, this is your semi insulating, so this part cannot conduct, your total channel is W, and you can see that there is an asymmetric distribution of the depletion width. So at any point, actually not, this is not x, this is actually y, sorry, this direction is x and this direction is y. So the fact that they are calling it Wx is actually at any point x, what is the width? So this is Wx, okay. So at any point the depletion is Wx, so the conducting area is only this. This is the conducting area, which is H minus Wx. At any point x, okay, x is in this direction, at any point x, H minus Wx is actually the conducting width. So you have to carry the current, you have to multiply that, of course the width of the channel is W, right. So if you multiply that with W, or in this case Z, they are considering it as Z, many textbooks consider it as W or Z. So H minus Wx divided by Z, because W, they are using W as the width of the channel, or width of the depletion, okay, H minus Wx into Z, this gives you the cross sectional area at that particular point x, which is able to carry current. You multiply that with the charge, which is Q times the doping, okay. So this is the charge, this is essentially the charge density essentially, and this is the cross sectional area. So if you multiply the cross sectional area into the charge density, you get the total charge, correct, and then you multiply that with the mobility times the field, So it's conductivity times the electric field, the charge times mobility is the conductivity, so mobility times field, and field is dV by dx. So the field can keep varying along this direction, so dV by dx is the field. I am assuming the mobility is independent along this x axis, okay. And from basic electrostatics of a Schottky junction, we know that Wx at any point x can be defined as this, 2 epsilon by q and d into Vx. Vx is the potential dropping across the channel at any point x, Vbi is the built in voltage, Vgs is the gate voltage that you are applying, okay, and this is square root, of course, alright. So because this Vx exists because there is a drain voltage, okay, at the edge of the gate here the Vx will be equal to Vd, because you are essentially approaching the drain, assuming this distance is negligible, okay. So this is your expression for Wx. So what happens is that you can integrate this equation now, you can integrate this equation and get the expression for the drain current. Here we are assuming that the mobility times field, okay, it holds true for the entire range. We are not considering velocity saturation anywhere, for any arbitrary electric field this holds true is an assumption we are making, overestimating though by the way, but if you integrate this you get this expression for a drain current. G naught is a term, basically it is a charge times mobility times doping times the channel width in terms H, which is the total channel thickness, divided by L, which is the gate length, Vds minus blah blah blah. So do you get, and V pinch off, of course I talked to you, V pinch off is this quantity is V pinch off, okay. So that quantity is V pinch off. So you get an expression like that, okay. So to increase the current, for instance, the mobility should be high, the gate length should be low, the width should be high, the channel thickness should be high, the doping should be high, etc., etc., if you want to get a higher current, okay, in this kind of a device, right. Now what is the condition under which the velocity saturation will occur? The velocity saturation will occur when the drain side pinches off, and that happens when this condition is met, okay. So how did this condition come up to be? So if you just consider Vp, that is the total voltage drop that can happen across the channel, minus Vbi, this gives you the total amount of gate bias that you need to apply to turn the device off. It is also called the threshold voltage, correct. In that case, in the example we took 1 minus 4 volt, 4 volt is the total drop if you can sustain, 1 volt is the built in voltage, so it is minus 3 volt. Minus 3 volt will be the, for instance, your threshold voltage. This is called threshold voltage. Now at threshold voltage you pinch the channel off completely, however you have a drain voltage here, a Vd here. So the drain voltage modifies the depletion and you have a wider depletion towards the drain and narrower depletion towards the source. So to have the wider depletion towards the drain, okay, what will happen is that your gate bias also comes in the picture. How much gate bias you are applying, okay, how much gate bias you are applying, alright, to get the channel drain pinch off, right. So how much bias are you applying to get the drain pinch off. So this expression tells you that your drain is actually the drain pinch off happens at that voltage of VTH plus VG. Okay. It happens at a range of VTH plus VG, and that is the voltage of the drain at which you will have your saturation current, because this is where the pinch off will happen. Okay. This is where your pinch off will happen. So, for instance, this value is -3 in this case, this value is -3 in this case, and if your gate voltage, okay, the VT, this is actually the negative Vp minus Vbi is actually the negative of VTH, correct, because the VTH is nothing but built in voltage minus V pinch off. So, this was 1 volt, this was 4 volt, this is -3 volt. At -3 volt your channel will turn off, we call it threshold. Here you have Vp minus Vbi. So, Vp minus Vbi is actually negative of threshold. So, this is minus threshold. Okay. So, essentially you have VGS minus VTH, which gives you the total voltage at which this is the drain voltage at which the channel saturation, that the current saturation will happen. So, in this particular case, for instance, you will have this quantity will be plus 3 volt, minus 3 volt is plus 3 volt, right. So, if your VGS, the gate voltage they are applying is suppose minus 0.5 volt, then the drain the point the drain current will saturate at a corresponding drain voltage of minus 0.5 plus 3, which is equal to 2.5 volt. Okay. If you apply, if you keep it say minus 1.5 volt, okay, then it will be at a 1.5 volt. So, the more negative the gate voltage is, the more smaller is the drain voltage at which the saturation happens, which is precisely what is shown here. Okay. I do not know if I go into the image here, you see here the saturation is here, 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 here. So, this saturation point actually follows this square law at a more negative voltage. So, this could be minus 1.5 volt, this could be minus 0.5 volt, just giving an example, You see the saturation is happening here, whereas for this the saturation is happening here. So, the saturation happens at a larger voltage when your gate voltage also is larger. Essentially what is happening is that you are taking care of the gate drain voltage drop, you are accommodating that gate drain voltage drop in calculating the pinch off, that is what is happening, and that is why you are doing that. Okay. So, if you see here, if I plug in this value of VD set, then I get this expression of drain current, okay, where I essentially replace this with this value. Okay. If I do that, I get this value, you know Vp, Vp is the pinch off voltage, and this is Vg, this is Vb. So, I get a very beautiful expression for saturation current. So, this expression will tell you that current is initially linear and then current initially saturates. So, I hope this part is clear, where like why the current saturates in terms of the drain pinch off, there is a small opening, the carriers have a local velocity saturation, any voltage beyond that, this part is dropping in a very small region here because of the hyperbolic dependence of the field, okay, and the current saturates, and your channel opening is fixed, it cannot open beyond that, it cannot close beyond that. So, that is the current saturates there. Okay. So, this is in terms of your how the IV characteristics look like, and this is the output characteristics of the device, and as I told you, the transfer characteristics is basically ID versus your Vg, in which case at some negative voltage the current will turn on and it goes like that. So, these are depletion mode devices because you have to apply negative voltage to turn the channel off, and the derivative of this current with respect to voltage, this derivative of this is called the GM, which is also called transconductance, and this transconductance is an extremely critical figure for microwave application. So, the transconductance will typically look like, it typically looks like this, okay, GM, you typically look like that. Okay. So, we will come to the GM also in subsequent discussions, but what we went through now right now is the physics of how the velocity the local velocity saturation and the carrier the drain pinching off leads to the channel current also exhibiting saturation. Okay. And the GM, the transconductance that I just told you, the transconductance is an extremely important figure because it will significantly determine your low noise performance. It will also determine significantly your gain in the device, and that is very critical for not only low noise amplifier but also for power amplifier. A higher GM is always desired, and a higher GM means that your channel control by the gate is excellent. Okay. And a higher GM also means that you will have lower noise, you will have high frequency advantages, you will have higher gain, so that is also good for power amplifier. Okay. So, high GM is always desirable and a high GM can come from a shorter gate length L. It also comes from shrinking the device dimension, bringing the gate closer to the channel, shrinking the source dimension, the spacing, etc., etc. A GM is really important, a high GM is really important for a good microwave device, whether it is a power amplifier or a low noise amplifier. Okay. And in the previous expression, if I take a derivative and I see, then the GM comes out to be this term G naught. I already discussed G naught is this term is G naught, okay, which depends on mobility. So, you can see that for improving GM I need to improve G naught, which means I need to improve the mobility. So, you always need material with higher carrier mobility. Doping can be increased, but the significant increase in doping can lead to reduction in the breakdown voltage, okay, with higher doping. Gate leakage also can increase. So, we do not increase the doping arbitrarily. You can increase the gate width to increase the GM, you can increase the thickness of the channel, this thickness, but again if you have very thick channel the gate will lose control. You can reduce L, which means you can make the gate short. So, all these things will help improve the GM, and you can see that it depends the square root of this term also, of course. Okay. So, this is about the current saturation, the basic operation of MESFET, about GM, about IDVD, okay. And this brings us to the conclusion of lecture 15, where we just introduced about MESFET, gallium arsenide MESFET, and the basic working mechanism of a MESFET in terms of the current voltage characteristics, in terms of the transconductance and the physics of the universality of FET's electrostatics, which is also applicable for HEMTs, MOSFETs, JFETs, etc. Other kinds of transistors also have the same physics in terms of current saturation. Okay. So, this was the basic introduction to MESFET. Going ahead we will talk about in more details about MESFET, and thank you for your time. This is the conclusion of lecture 15, and in the next class we will see you in lecture 16. Thank you.